So we're going to let f of x be defined for all x, but maybe not a, because we're not, the limits as approach, but don't get there. For all x, but not a, over an interval containing a. I'll draw a picture of what all this means in a sec. And then we're going to let L be a real number so that the limit as x goes to a of f of x is L, right? So L is our limit. And again, for a limit to exist, it's got to be a real number. If infinity pops up, that ain't a number, so that doesn't count. So for every epsilon, so that's the little Greek epsilon there, greater than 0, there exists a number called delta, so that's the Greek delta, that's also greater than 0, such that if x minus a, so the difference, the distance between x and a is between delta and 0. So if x is some number close enough to a, and I'll explain that more in a sec, then the distance between f of x and L, right, so absolute value helps us find that distance here, that's going to be less than epsilon. I'm going to draw a little picture of this off to the side here. And let's suppose this is our function here, and we're zooming in at the place where x is equal to a. And, right, it doesn't have to exist there, function value, but we're approaching some y value L here. So this is my graph of f of x there. The epsilon right here, what you can consider that right there, it's a very small change in y. Because notice down here in this inequality, I say take the function value, we plug in some x value, subtract it from L, and the absolute value means it doesn't matter which is bigger. We're just trying to find out how far apart these two are. So remember, the essence of subtraction finds the distance between two numbers. Okay, that's like the basic idea of what subtraction does for us. So this says let the distance between f of x and L be less than some number epsilon. And we get to pick that number. And this is the dare I was talking about before. So let's say, let's go that wide right there. So this right here is L plus epsilon at the top. And down here would be the y value L minus epsilon. And f of x over here is just some y value. So that's like saying y minus L, the distance between y and L. Epsilon is a small number, right? That's the goal here, to pick a little number because I'm zooming in, right? So we're just saying, hey, let these y value and the L value be close together. Now, if I trace these backwards, so if I take this, trace it over and down, and this one over and down, if the function is curved at all, then if one interval, like the y interval here, is symmetric about L, L is exactly in the middle here, the other one won't be symmetric. So you can see that in my picture. It's smaller on this, the left side than the right side over there. Now, usually, like over here, we talk about this number delta, and the number delta here, that's just a small change in x. Symbol for change, there we go. So what I'm trying to do is I'm trying to pick some x value over here. So let's say I pick that x value right there. This distance in between a and x here, right, that's the delta, the distance those two are apart. And what I want to happen is if I pick an x value close enough to a, and I trace back this way, and I look to see what its y value is, I want to assure that that y value is reasonably close to L over here. So the way it goes is like this. It's a dare. Someone says, okay, I need your answer, your result here, to be within 1,000th of the actual number. And so what I should be able to do is I should be able to then find x values so that when I plug them into the function, I'm within 1,000th of the actual limit. It's the way it works. Okay, so I say, hey, the limit is this number, and you say, prove it, can you get within 1,000,000th? And I say, yeah, try any of these x values, that's within 1,000,000th there. So we kind of squeeze the y values to be able to find x values that get us close enough. And we can do that all day long. So someone else says, no, I need you to be within 1,000,000th, and I do a little calculation. I can say, okay, any of these x values would give you within 1,000,000th. So let's give it a try. All right, so using the definition of a limit. So we'll run through a few examples of this. So let's start off pretty easy. Let's let x equal, or f of x equal 2x plus 1. And we're going to let a, the x value, be -1. And let's let epsilon to start with be, how about 0.2 tenths? So we just have a pretty low level for how close we have to get there. So based on at least the first two pieces of information, I can say, all right, the limit as x approaches -1 of 2x plus 1 is what? Well, plug in -1, we get -2 plus 1, it is -1. So that's what we think L is right there. And then someone says to me, oh yeah, if L is -1, give me some x values that get me within 2 tenths, right? 0.2 is 2 tenths. So the way it works is we start off with the latter part of the definition, the part that says f of x minus L is less than epsilon. And our goal is to turn that into the absolute value of x minus a is less than delta, so that we can discover delta. So starting with this right here, I get the absolute value of 2x plus 1 minus -1, right? Because it says minus L, L is -1. We want that to be, that distance to be less than 2 tenths. And I want to apply a little algebra to make it look like that. Okay, so what do I have to do to make this look like x minus a? Actually, what is my a here? My a is -1, so x minus -1 would be x plus 1. Let's state it the right way first. It's less than delta, and I should be able to discover delta there. Now, x minus -1 is the same as x plus 1. But the way I wrote it above with the absolute value, a reminder about the interpretation of this right here, means the distance between x and -1. Okay, so whenever we take the absolute value of a difference, that finds the distance between those two numbers for us. So cleaning this up right here, let's see, what do we get? We get, let's switch colors, 2x plus 1 plus 1, 2x plus 2 is less than 0.2. And then, hey, I can factor out a 2 here. So this is the absolute value of 2 times x plus 1 is less than 0.2. And since 2 is positive, it can pop out of the absolute value. So this can be written as 2 times x plus 1 in the absolute value is less than 0.2. And notice, I'm getting very close to that sucker right there. If I just divide both sides by 2 here, I got it. So dividing by 2, x plus 1 in absolute value has to be less than 0.1. And I want to take a look at the graph of this to see if this is reasonable. So it looks like, in words, if we want f of x to be within 0.2 units of -1, then x should be within 0.1 units of, and coincidentally, x is -1 when y is -1 here, -1. And so let's take a look at that on a graph. So I think I'll try graphing this by hand. It's not too bad. And I guess we have to zoom in slightly, but not too much. 1, 2, 3, 4. Why am I marking that like that? 1, 2, 3, 4. So I'm going to go over here for x is -1, and then 1, 2, 3, 4. Let's go down here for y is -1. And so this is our point of interest right there. So that would be 1 right there. And that would be 1 over there. So the slope is 2. So if I go up 2 over 1, then I should have another point there. So let's graph this sucker. Let's see, up 2 over 1. Maybe it starts there. So here is the graph of my functions. Let's label some stuff. This is my y-axis, my x-axis. This right here is my f of x equals 2x plus 1. And again, we're exploring here graphically now the limit as x approaches -1 of 2x plus 1, and we think that limit is -1. And this is not the best zoom, but we're just going to go for it. So we're going to say, like, this right here are the boundaries I'm setting for delta. So here in the middle is x equals -1. And so x could be on the left side or the right side. So this interval right here is x is between -1 plus delta, delta, and -1 minus delta. And I'll explore that idea just a minute. And if I trace those y values over, then these right over here are my epsilon distances. So up here would be the plus epsilon, and down here I'm going minus epsilon. And so this number right here would be, for example, -1 plus whatever epsilon is, and this one down here would be -1 minus epsilon. Boom. Epsilon. So this whole interval right here are y values that are between -1 plus epsilon and -1 minus epsilon. And so with a linear function, both intervals are going to be symmetric. If it's curved, they're not going to be symmetric there. And again, we want epsilon to be a small number. 0.2 really isn't that small, but the goal is to kind of squeeze in. So as we squeeze in toward the limit, the x value should also squeeze in here on the graph. So that's kind of a graphical exploration. So as we narrow this vertical range here, right, we're zooming in on the point. So this is a technical definition of what it means to zoom in and to define numbers to do that. So let's try another example. How about, let's throw some fractions in there. So suppose we let f of x be 2/3 x, and have a -1, and let's let x or a equal 3. And then we'll start off with an epsilon of 1/10. Oh, let's go even smaller. The problem is once I can't draw 3 and 100th on the same scale easily and see the x and y axes. So graphically, it's a little harder to envision this, but we're just going to do the algebra here. So again, the way this starts is we write our limit if it's not already given. So the limit as x goes to 3 of 2/3 x minus 1 is equal to, if we plug in 3 here, what do we get? 2, we get 1. So the limit should be 1. So that's my L. And then again, the way we start is write down f of x minus L is less than epsilon. And what we want to do is do some magic algebra to, so our goal is to change that into x minus a is less than delta. And so I usually like to write both the original and the goal with the actual numbers. So that's going to give me 2/3 x minus 1. And then minus 1 again for L. So here's my f of x, right? And there's my minus L. Inside the absolute value is less than 1/100th. And I need to get that to look like x minus 1 is less than delta. And then I should be able to figure out what delta is once I clean this up. So we apply some algebra to this right here. So let's see, what do we get? 2/3, oh shit, no, I did something wrong. What's my a here? It is not 1. My a is 3. Okay, so 2/3 x minus 1 would be minus 2 is less than 0.01. And I'm going to approach this a slightly different way just for fun. Last time I didn't get rid of the inequality. This time I'm going to. So hopefully you remember dealing with inequalities from your algebra days. If you have an inequality that is a less than something, and we do, we have 2/3 x minus 2 is less than 0.01. To get rid of the absolute value, you have to take that middle term, the middle function, 2/3 x minus 2, and that becomes less than 0.01. There's one version of it. Or let's see, no, and 2/3 x minus 2 is greater than negative 0.01. And if you put those two together, the cleaner way to write it is that 2/3 x minus 2 ends up being between 0.01 and negative 0.01. So it might have been a long time since you did that in an algebra class. And the rule is if you have an absolute value inequality, if it's a less than, the connector is and. If it was a greater than, the connector would be or. And if you read this from the variable, so over here, I read from the variable 2/3 x minus 2 is greater than negative 0.01, which is exactly what that says up there. Right? But this is the more concise way to write it as a compound inequality. Now to solve this right here, I just treat it like a regular algebraic thing, but when I add the 2, I have to add the 2 in all parts. And so that cleans up a little bit to 2/3 x is less than 2.01 and greater than 1.99. And you can see kind of we're looking on each side of 2 here. And then to convert this to y values completely, I have to get rid of the 2/3. So we'll multiply both sides by 3/2, or all 3 sides by 3/2. Blue. Okay, so that gives me x is in between those 2 numbers right there. So I guess I need a calculator for those. But I'm not quite done here because I have an x in the middle, but my goal back here was to have an x minus 3. So one more step before I whip out my calculator. I want this to be a minus 3 right here. So that means I have to do a minus 3 on each side with those guys. So let's do it. Calculator. And let's use calculator's fine. All right, so on the right side, I have 2.01 times 3/2, and then minus 3. Is that right? Yep. So that's 0.015 on one side. And check out the other side. So on the other side, I have 1.99 times 3/2 minus 3. Whoa, well, look at that. It's negative 0.015. Interesting. Now, since these match, that's pretty fortuitous because now I can rewrite it as an absolute value inequality. X minus 3 has to be less than 0.015, and I have discovered my delta there. So a slightly different way to look at that algebraically would be to not break the inequality, which into its pieces like I did before. If I factor out that 2/3 there, it gets kind of interesting. So if I try to pull out 2/3, then that's kind of like factoring is like dividing. So that's like dividing this by 2/3, dividing that by 2/3. Negative 2 divided by 2/3 is negative 2 times 3/2. And so that's going to give me an x minus 3. To check that that's true right there, if you multiply the 2/3 back through, what is 2/3 times 3? Well, it is 2. So that checks out. And then I can take this 2/3 and multiply by the reciprocal on the other side. And that's going to give me x minus 3. It's less than 0.01 times 3/2. Now, 3/2 is 1.5. And if you take 1.5 times 0.01, then you're going to get 0.015. Which is the number we found on the other page. So sometimes when I'm doing these, I'm able to keep the absolute value there intact and just kind of play around pulling stuff out and moving it over. Other times I don't see that idea there in my head. And so I have to split it into this trifold inequality. So it just kind of depends on the problem. We got to play around and see what happens. All right, let's do a harder one. Oops. New page. There we go. Let's try a quadratic equation. So let's start off with the limits as x goes to 6 of x squared minus 12x. And if we plug in the 6 there, what's going to happen? We're going to get 36 minus 72 is negative 36. So that's the limit. So this right here, x squared minus 12 is our f of x, the 6 is my a, and the negative 36 is my L. So I'm going to go and write this in the precise definition form. And so then, remember, the first thing we do is we write f of x minus L is less than epsilon. Oh, and I guess I need an epsilon here. Actually, we're going to leave epsilon, epsilon. And in the definition, it says epsilon can be any number less than 0, greater than 0, and it's supposed to be a small number. So epsilon is just some small number here. It could be 100th, it could be a millionth, it could be a billionth. Okay. Have a little more fun. So plugging in, what do we get? We're going to get the absolute value of x squared minus 12x. Let's see what comes next, minus L, which is negative 36. So be careful with your signs. And it's just an epsilon. We're not going to give it a number there. Remember, the goal here is to take that thing and make it look like x minus a is less than delta to discover delta. And so that means the goal we have here is to make that thing look like x minus 6, 6 is my value for a, is less than delta. All right, what do we got here? That gives me x squared minus 12x plus 36, which factors as x minus 6 times x minus 6, or x minus 6 squared. So put the absolute values back in here. Now, something to consider, if you square a number, it's always positive, so I really don't need the absolute value. So this is equivalent to x minus 6 squared is less than epsilon, since x minus 6 squared is always positive. To solve that, I would take the square root of each side. And so if I take the square root, let's see, what do I get? What's the square root of x minus 6 squared? Kelsey says x minus 6. You are so close. It's almost x minus 6. There's a slight tweak we have to make. So close. All right, so check this out, you guys. So off to the side here. Suppose I take the square root of the square of 5. What should that be equal to? 5, right? But suppose I take the square root of the square of negative 5. What's that equal to? Well, that's 5 also. So when you take the square root of a square, you don't always get back what you started. So it turns out the square root of the square of something is the absolute value of that something, whatever that something was. So back here, technically, this resolves to the absolute value of x minus 6 is less than the square root of epsilon. And that is wicked cool because that is my goal right there. So this just tells me that I should let delta be the square root of epsilon. So if somebody says, hey, let epsilon, for this example, let epsilon equal 0.0001, then I would say, cool, then delta is going to be the square root of 0.0001. And that's that. So the moral of the story here is applying the precise definition is hard. It took me a while as a student to wrap my mind around the precise definition of the limit. I'll talk about it more tomorrow, but you should definitely start some of this homework ASAP to help better understand this. And for linear functions, it's pretty straightforward. It always works out nice. If you try it for any other kind of function, then you got to get a little more creative in your algebra. I was lucky that last one, let's see, by tomorrow you mean Monday, right? Oh, what's today, Thursday? I lose track of the days in the time of COVID. Yeah, today's Thursday. Oh no, and then Monday is MLK Junior Day and there's no school. We don't get to do math again till Tuesday. Oh my gosh. Is that really true? It is true. Bummer. I am sad to hear that. Okay, so wait, we don't have school Monday. Yeah, that is correct. So let's go back and look at, so there should be no classes on Monday. So let me make sure I'm not making stuff up and lying here. First thing, I just want to check the calendar I posted for the class. So daily work schedule, get back here. Yeah, MLK Junior Day is the 18th. There's no classes at all that day, to the best of my knowledge, and I'm just going to double check my knowledge. So go to the BMCC homepage and check out the academic calendar for 2021. And we are what, winter quarter days we are closed. Yeah, Martin Luther King Jr. Day, January 18th. There are no classes at all on Monday. Cool. All right, so Monday is a do your own thing day. And we don't get to resume math together until Tuesday. So we are kind of done, at least I'm done with my main ideas about chapter 2. The next thing is you guys gotta get your homework caught up, and I guarantee there's gonna be questions on 2.5. 2.5 homework, however, is not due until the 14th because we have all that time off between now and then. Let me make sure I'm not lying about that. 2.5 is due. I set it to the 15th. I gave you an extra day there. Please don't wait till the 15th to start that. You'll have forgotten everything we talked about today. Oh, I'm lying. Today. Oh, today's the 14th. I knew that. So it's due tomorrow. And yeah, if anyone needs more time, I'll extend it. But for now, I'm going to leave the date at the 15th. And if you get stuck, message me through the homework system. So if you whip out, oh, there's one problem that's wicked cool I want to point out right now. And sorry, I know it. I got to shut up. I'm out of time. I'm so bad at that. Sincere apologies, but math is so much fun. Question 6 has a link to Desmos. And this is the coolest thing ever. Somebody else built this. I didn't build this one. They built a graphical version of the epsilon here and the delta here, and you can plug in any function you want. Now, the hard part about that, however, is if you plugged in that function we just did, x squared minus 12x, and then you said let a be 6, that's what it was, right? Oops, I didn't mean to hit enter there. Then you have to go zoom over to that point, which is like way over and down. And sometimes the graphicalness of it falls apart at that point. So it's not necessarily useful for all functions. I kind of just totally messed this up now. But for some of the basic ones, it's pretty good. So you plug in your function, you plug in your value for A, it calculates L for you, and then you can play with delta and see what epsilon looks like, which is pretty awesome. So that could be useful for some of the other problems before number 6. All right, it is time for me to officially shut up.